As I'm standing here out in the sun, I'm bombarded by a shower of cosmic particles produced in the nuclear reactions inside the sun and other stars. Today's news from CERN is about the lightest and most abundant of the cosmic particles, neutrinos. Every second, some 60 billion neutrinos produced in the sun pass through every square centimeter. Today we know there are three families of neutrinos: electron, muon and tau neutrinos, and that they oscillate between one family and another. This process is only possible if neutrinos have mass. But neutrinos do not come only from above. In this very spot, 50 meters below my feet, a beam of billions and billions of neutrinos is produced every day by one of CERN's accelerator, the SPS, the Super Proton Synchrotron, located 50 meters right below my feet. In less than 3 milliseconds, the neutrino beam produced by the SPS reaches its target, the OPERA detector, that is located, well, quite far from here, 732 kilometers in that direction, across the Alps, under the Gran Sasso Mountains, in central Italy. The beam leaving CERN consists entirely of muon-type neutrinos. By the time it reaches Gran Sasso, some will have oscillated into tau-type neutrinos. Neutrino oscillation happens over a very large distance, which is why the experiments designed to study the oscillation are placed 730 kilometers far from the beam source at CERN.
The OPERA detector is made of 200,000 special bricks, each of them containing 50 sheets of lead and 50 sheets of emulsion, a special substance similar to photographic film that can record in a very precise way the passage of particles coming from the interaction of a neutrino with one of the bricks. The difficulty of this experiment is to determine in which brick the interaction took place, and to do this we put layers of detectors called scintillators between each layer of bricks. These scintillators record the passage of the particles in real time.
Let's now find out more about the tau neutrino observed by OPERA by talking to the spokesperson. So we are here in front of the control of the SPS accelerator that sends neutrino to OPERA with the spokesperson of OPERA, Antonio Reditato. What has OPERA observed?
Well, OPERA has observed its first tau neutrino candidate event. We are confident that this is a very interesting event, and of course we need more to fully assess our aim, our goal, which is the discovery of neutrino oscillation in appearance mode. This is the main task of the OPERA experiment. The discovery of neutrino oscillation is by now quite established. This was done in 1998 with the Super Kamiokande observation of oscillation with atmospheric neutrinos. Since then, many experiments have tried and successfully managed to observe disappearance of neutrino oscillations. So you basically start with a certain number of neutrinos, and then you find that this type of neutrinos is not exactly the same number that you get at the end.
It's less.
Is less. So there is disappearance, as we say in jargon. What we want to do with OPERA is to detect the appearance of the different flavor. So we know that we start with muon neutrinos, and we will get eventually some tau neutrinos. And we want to detect these tau neutrinos. When a tau neutrino does something in our detector, produces a tau lepton, and we detect this tau lepton. So this is the first event which is compatible with the detection, with the observation of a tau lepton.
is the distance between the origin of the beam here at CERN and the opera detector at 732 kilometers from here under the Gran Sasso mountain a difficulty for this experiment?
Well, actually, from the point of view of the number of events that you get, it is a complication. In the sense you start from CERN with a lot of neutrinos, and of course they spread out, okay? And just a few of them go through the detector. But of course this is a need. We do need such a long distance, because neutrinos, in order to oscillate, they need a sort of minimal distance given their energy. And actually I would say that it would be much better if the Gran Sasso laboratory was a little farther than where it is, but it's already very good like that. So distance is not an issue, on the contrary, it's what we need.
The idea that a neutrino could oscillate from one type to another, and that the different types of neutrinos were nothing but different states of the same particle, is due to Italian physicist Bruno Pontecorvo. Pontecorvo noted that the rigid classification of neutrinos in 3 different families would be true only if the neutrino's mass was 0. If the neutrino had a mass, it could be a mixing of the 3 families, electronic, muonic and tauonic. In this case, it would be possible to see the neutrinos oscillate, that is, turn into the next family.
The oscillation neutrino obviously is a phenomenon already studied and well known in the last decades, but the importance of this event by the opera experiment is due to the fact that it is the first direct evidence of oscillation of neutrino. In this sense, we can definitely rule out other possible explanations of the disappearance of neutrino already measured in other experiments.
The effect the opera experiment is looking for is extremely subtle. Of the billions of muon neutrinos leaving CERN, just about 15 of those that oscillate can be detected over the lifetime of the experiment. This will, however, be enough for scientists to complete another part of the neutrino puzzle.
Neutrinos are mysterious and very fascinating particles, and we have now the first tau neutrino candidate event, which is a very clean event after, well, 10 years after the proposal and 13 years after the first conceptual idea. We expect to have more events. I hope they will come soon, but the experiment is certainly very challenging.